Okay, good morning. Let's get started. So we are continue our discussion on steady diffusion discretization for unstructured non-orthogonal meshes. Okay, so this is steady diffusion on unstructured non-orthogonal meshes. Okay. Fine. So, what the equation that we have kind of derived is basically sigma f gamma grad phi f dot a f plus S c plus S p phi 0 times delta V 0 equals 0, right. That is the equation we have, and we are working with the diffusion flux term, and the diffusion flux term we have seen that we can write this as gamma grad phi f dot a f as some quantity, right, some quantity times phi xi f, right, that is the gradient in the xi direction, plus some other quantity times phi eta f, right. These specific quantities we have derived in the previous lectures, right. So, we have done that, decomposed this into the xi direction and the eta direction, and then what we said is, of course, the derivative in the xi direction can be written in terms of the cell values, right, using a linear profile assumption. Phi xi f can be written as phi 1 minus phi 0 upon delta xi, right, that is what we have said, and we called this first term which is multiplying phi xi f as the primary gradient, right. So, this we said as the primary gradient, and the second term we said this is our secondary gradient. Okay. Now, we devoted a considerable amount of time in understanding how to calculate the secondary gradient itself, right. So, this term itself. Now, the secondary gradient term we denoted using S g sub f. This we said actually will come out to be minus gamma f a f dot a f by a f dot e xi, right, that is what we have, and times e xi dot e eta times phi eta f, right. This is the coefficient that we will have for the secondary gradient, and we said calculating this would be straightforward if you have any 2D mesh, whether it is structured or unstructured, or if you have a 3-dimensional structured mesh, right. Whereas, if you have a 3-dimensional unstructured mesh, then selecting the two directions on the plane, right, which is eta and zeta may not be unique. As a result, we may not be able to find it in one particular way for all the cells, right. So, we said okay, then one good way to calculate this is basically somehow we can calculate the total phase gradient and then subtract off the component of the xi direction from this total gradient, right. That is what we kind of wrote this. So, if we have a, let us say in general a 3-dimensional unstructured mesh, then we said the secondary gradient can be calculated using gamma f grad phi f dot a f. So, this is the total transport of phi, right, through the phase f, and we said this minus the gradient in the primary direction, right. So, that would give you what is the gradient, whatever is the transport in the secondary direction. Okay. So, this minus the gradient in the primary direction would be gamma f upon del xi f a f dot a f upon a f dot e xi times we said grad phi f is what we would calculate on the phase. Then, if we were to subtract off the gradient in the primary direction, this would be e xi, right, that will give you the value times delta xi, right, that is your term. So, this is your primary value, and this term is your total gradient on the phase, right. Okay. So, essentially the total minus the xi direction will give you the entire secondary gradient term, that is this term, right. That is what we said. Of course, now we said we do not know the phi value itself, that is the unknown, but we are now talking about calculating the value of gradient of phi, right. So, which needs to be somehow computed on the face. So, now the calculation of secondary gradient is reduced to the problem of calculation of gradient of phi on the faces, right. If we can somehow calculate the gradient of the phi on the faces, then we can calculate the secondary gradient term, right. Again we say that using an approximation, if we have, if the gradient of phi can be assumed to be constant in a cell, if it can be assumed to be constant in any cell, then the gradient on the face can be written as an arithmetic mean of the gradients on the cell values, okay, because grad phi itself will be a constant over the entire cell, right. Then the average of these two would give you the gradient on the faces. Okay. That means we have to somehow calculate this gradient at cell centers, right. So, essentially for all the cells we have to somehow calculate this gradient. Okay. This we will see little later how to calculate this, we will address it little later. As of now, if there is a method by which we can calculate the gradients at the cell centers, we can calculate the gradients at the faces, which further can be used in calculating the secondary gradients. Yes. Why arithmetic mean? So, essentially you have two cells and the gradient is assumed to be constant over these entire cells. So, then the face value could be taken as the arithmetic mean of these two. Yeah. So, we are assuming that this grad phi remains a constant over the entire cell. Yes. So, this distance. So, even if it is not equal, what is grad phi? Grad phi is assumed to be constant over the entire cell, right. I am assuming that it is constant. So, whatever is the distance, it does not make a difference, right. So, for example, even if I have a, if there is a variation of grad phi inside, then there will be an effect of the distance, right. I am assuming that grad phi is constant over the entire cell. So, wherever I go, whether I come here, I go here, wherever I go, it will be the same value, that is what I am assuming, right. Grad phi is a constant for the entire cell. As a result, I can take an average, right. Now, if it is not constant, then of course, you have to take a kind of a linearly interpolated value. Okay. Other questions? Is it clear the concept of coming to the concept of gradient of calculations, gradient of phi from the motivation of the secondary gradients, right? Okay. Fine. Okay. Then let us move on. All right. So, we have all these values. Then let us try to write a discrete equation, okay, which will be for non-orthogonal meshes. Okay. So, let us assemble all these things and write the discrete equation for non-orthogonal meshes. Okay. So, just like before, up till now we have been talking about, let us say, one face f here, right, but actually you would have several faces and several cells, right. You will have another cell here, another cell here. As a result, you will have, this could be f1, this could be f2 and f3. You would have cells c2 and c3 and so on, right. You will have several cells and several faces. So, you have to do a summation of the gamma grad phis, right. So, that has to be done. So, that we have to do it, because we have only dealt with one particular phase between C0 and C1. Okay. Then if we write similar equations for each of the phases and then kind of assemble them. So, considering all phases f, okay, for the cell, and then assembling them, we would write the equation, the discrete equation for the cell C0, right, and we would like to put it in the standard form, that is our AP phi 0, right, AP phi p equals sigma a and b phi n b plus b, okay, where a and b's are the coefficients for the neighboring cell values. So, those will be given as a and b would be what? Would be coming from your primary gradient, right. So, whatever was this primary gradient, how much was this? This was gamma f upon, so this entire term, right, we wrote it as gamma f by del xi f a f dot a f by a f dot e xi times phi 1 minus phi 0, right. This is what we have written. That means, what is the coefficient here? This entire term in the parenthesis is the coefficient that is going into a and b, right, that is for as the coefficient of phi 1 a 1, and then this is also going into a p as a coefficient of phi 0, but a p terms would go to the right hand side, right. So, what would be your a and b now? A and b is just this term, right, and is what we have to write. So, that means a and b would be gamma f upon delta xi f a f dot a f upon a f dot e xi, where f is for the phase when you consider C 0 and the neighboring cell, right, and the neighboring cells are 1, 2 all the way to, let us say if we have m neighbors, then this would be the phase f between C 0 and that neighbor, right. C 0 and C 1 could be the phase f, between C 0 and C 2 could be f 2 and so on, right. So, we have several of these, that is your a and b. We do not have any contribution from coming from the secondary gradient, right, into the a p, because we said all the contributions coming from the secondary gradient would go into b term, okay. This will go into b, as a result we do not have anything there. Okay. Then what else will be expressions for a p? Summation a and b, because sigma a and b all the neighbors. What else will go into a p? Minus s, sp, sp delta v 0, right, that is what will go into a p. What will be the contributions for b? Secondary gradient, okay. Before that we have the source term also. So, sc times delta v 0, and then we have how many secondary gradients? Only one? Neighbors, right. So, essentially it will be summation of all the secondary gradients for all the phases, right. So, that could be plus sigma n b s g f, right. Would it be plus or minus? It should be plus, right, because the secondary gradients we have denoted it as plus, the minus entire thing we denote it as plus, and it remains on the left hand side, right. As a result, this is plus. Fine. Anything else, or is that all? So, the primary gradient went into a 0, a and b's and a p, secondary gradient went into b and the source terms, that is all, right. There is nothing left over. Okay. So, all these things are there. That means, if we look at it, the equation as such is very similar to the orthogonal system of equations, right. Even if we had an orthogonal system, we had a p phi p equals sigma n b phi n b, right. So, this is similar in structure to an orthogonal system, right. Okay. What about the the Scarborough criteria or the summation properties? So, let us say we do not have source terms. In the absence of source term, that means your entire S bar equals 0. What is your A p? Is A p summation of sigma A and b or no? Yes, it is. A p is summation of sigma A and b. So, Scarborough is satisfied in equality, okay, equality is satisfied. What about boundedness? Boundedness, that means you have source equals 0, right. So, essentially source is 0. So, this term is 0, this term is 0, then A p phi 0 would be sigma n b phi n b plus, is b 0 now? B is not 0, B has secondary gradient, right. So, that means phi p or phi 0 is not just sigma a n b by a p phi n b, right, which was the case in the context of orthogonal meshes, right. So, here our equation is phi 0 equals sigma a n b phi n b plus b upon a p, right. This is still not equal to 0 because of secondary gradients, right. As a result, is it bounded? No, it is not. Boundedness is not guaranteed, right. Now, what about SG? SG, what terms would go into secondary gradient? Some coefficient, right, times what is the derivative that is multiplying these coefficients? Partial phi partial eta, right, partial phi partial eta. Now, how do you calculate partial phi partial eta? Previous values, but those are also neighbors of these cells, right, but they may not be the face neighbors, they could be the vertex neighbors, right, are sharing the same vertex. So, as a result, SG will also have values from phi, right, coming into play, and these phi neighbors will actually contribute to the secondary gradient as well, right. So, in some sense we can think of the boundedness as not just by the face neighbors, but also with the cell vertex neighbors as well might be there, right. But the thing is, it is still not a, it may not be bounded because it is not, the property of sigma n b by a p equal to 1 is not satisfied for those coefficients, right. As a result, boundedness is not guaranteed, is not assured, right, because phi 0 is not just sigma n b by a p times phi n b, plus you have this b term which has the secondary gradients. As a result, boundedness is not assured, and we will see a little later that the computation of calculations of the secondary gradients will produce oscillations, okay, oscillations in phi values, okay. Essentially in the calculation of phi, when you use the secondary gradients, it will produce some oscillations. As a result, the boundedness is not guaranteed, okay. This we will see a little later. So, that means if you have a non-orthogonal mesh, that means boundedness is not assured, right. You can still have slightly higher values than your neighbors, right. Now, how do you get rid of this thing? I mean, how do you make sure that boundedness will always happen? Depending on the mesh you use, right. If you have a good mesh as close as possible to an orthogonal mesh, then you would have this boundedness criteria satisfied, right. Otherwise, you will still introduce some error in the solution, okay. There are several ways you can get rid of this problem by having limiters and things like that. We will see that little later in the course, okay. Yes, questions? In the context of, yes, if you have a steady state solution, it has to be bounded. That is what it should happen if you have a very good mesh, right. But in this context, if you have, if the mesh is has these problem with secondary gradients, then it need not be bounded, right. That is what essentially that is the problem with non-orthogonal meshes. The non-orthogonality will come into play as a numerical artifact, right. So, you will still get a steady state solution, it is just that it will not be bounded. It is actually incorrect because it is not bounded, but you will still get a steady state solution for that, right. Only way you can improve is either through having a better mesh quality, okay. Other questions? So, that means it emphasizes on the need for a good mesh to start with, right. The same thing if we had an orthogonal mesh, let us say Cartesian mesh or something, then you would have got like a beautiful result which satisfies the physics, right. Okay. Other questions? Okay, so, in this context we have boundedness is not guaranteed, but this Scarborough is satisfied, right. That is kind of there. Fine. Okay. Then one more thing that remains is basically looking at the boundary conditions in the context of non-orthogonal meshes. Okay. Up till now we have talked about any interior cell, right. Now, how do we do this for a boundary cell? Okay. So, let us look at extension of this to discretizing boundary fluxes. So, that is boundary flux calculation. Okay. That means, we are looking at a particular cell that has one face as a on the boundary, right. It could be one of the Dirichlet boundary conditions or any other boundary conditions that we have seen. Okay. So, I would draw here again a particular typical cell. So, typical cell is, let us say this way, and this is my cell centroid. The area vector is here, we call it A B bar, which is again pointing away from the cell, outwards from the cell, and this is our C0 cell, right. And the face centroid is somewhere here, okay. And the line connecting the cell centroid to the face centroid now defines the direction E xi, right. If it were interior, the line connecting the C0 to C1 defined our E xi. Now, we do not have an I-bar, right, because this is a boundary, right, and these are the interior faces. Okay. What about E eta? E eta would be tangential to the face as before. So, that means this is my E eta, and now again A B bar is need not necessarily be parallel to E xi, right. The line connecting the cell centroid to the face centroid need not be parallel to the A B bar. That is where we have a non-orthogonal mesh. Yes, question. Oh, sorry, this should be eta. Okay. Fine, good. Okay. Anything else? Okay, so this is E eta, we have E xi, and this is need not be 90 degrees. Okay. All right. So, that means, the discrete equation that we have can be written as sigma gamma grad phi f dot a f. Okay. This is over all the interior faces. I would like to call it as interior. Okay. So, essentially I am separating the diffusion flux for the interior faces, that is for, let us say this phase and this phase, and for the boundary phase separately. Okay. That means, plus I would have gamma grad phi b dot a b, let us call this phase as b. Okay. This is my phase b. So, the diffusion flux is now written out separately. That means, this summation, the first one only goes around how many phases here? 2 phases. Okay. So, plus we have SC plus SP phi 0 times delta V 0 equals 0, right. That is our discrete equation for a boundary cell. Now, do we know how to calculate the first term here for all the interior faces? We know, right, that is what we have been discussing till now. So, this is already know how to discretize this thing, know this thing, fine. So, only thing we have to discuss is the boundary term gamma grad phi b dot a b, right. Now, this will be very similar to what we have done in the context of an interior face, but with very few subtle changes here and there, which we will see. That means, we have to now discuss how do I calculate gamma grad phi b dot a b. Okay. So, again this can be written in terms of 2 gradients, right. One is along phi xi and one is along phi eta, just like what we have done for any interior cell, right. So, the same steps follow, right. We have done whatever we have done for the interior face can be done for the boundary face, right. Only thing is that instead of A f you have now A b, okay. And of course, how do you define the distance here? What is delta xi? Would be the distance between the face centroid and the cell centroid. This is like your delta x by 2 if you had a Cartesian mesh, right. So, this is basically delta xi b, okay, which will connect the cell centroid to the face centroid. Okay. Fine, all right. Then I can again decompose this into 2 components, one is along phi xi, other one is along phi eta, and I can write the same thing, that would be gamma b, okay, a b dot a b by a b dot e xi, right. That is the first term I have, times phi xi on the face b, right. That is the first term, primary gradient I would get, minus I would get gamma b AB dot AB upon AB dot E xi times E xi dot E eta times phi eta B, right. Those are the two components we would get if you follow the same process we have done for the interior phase, with only changes being you would use AB instead of AF, right, for a boundary phase. Fine. Okay. Then what about the first term? How do we calculate phi xi B? Because we have a boundary phase, just like the structured or the Cartesian meshes, we would also somehow store a value of this on the face, right. We would also store a value irrespective of the boundary condition. The boundary condition can be a Dirichlet, a Neumann or a mixed, but we will still store a value of phi on the face, right. You remember, if it were Dirichlet, of course phi B would be known. If it were not Dirichlet, we would somehow calculate it, right, by the balance of the fluxes. So, phi B on the face will be stored and it will be updated, and we also know what is phi 0 at the cell centroid C 0, right. Now, how do I calculate partial phi partial xi on the for the boundary phase? Phi B minus phi 0 upon delta xi B, okay. Fine. So, we have this thing, that means what about the primary gradient term? If I write it here, this would be gamma B by delta xi B, AB dot AB by AB dot E xi times phi B minus phi 0, right. That is what we have, isn't it? That is the primary gradient. Okay. What about the secondary gradient? Now, how do we calculate this guy? This is our secondary gradient. Essentially, we are burdened with the same problem as we had with the interior faces, right. That means, again, if it is a structure, if it is a 2D mesh, we can of course somehow calculate phi eta B along the tangent. If it is a 3D structured, again we can somehow calculate it, but if it is 3D unstructured, then we have to go to this business of calculating the total value minus subtracting the primary gradient, okay. So, we will do all that. So, that means calculation of secondary gradient for boundary is also the same thing. So, if it is 2D structured or unstructured, this can be calculated using interpolation. If it is 3D structured also, this can be calculated, but if it is 3D unstructured, then we do not have a unique way of defining the two secondary directions. As a result, we will resort to calculating the total minus the primary, okay. That is going to give us the secondary, okay. So, we will resort to a new different method. Now, that means I can rewrite the secondary gradient as what? If I were to write this as G of B, this can be written as the total transport of phi through the boundary phase, that will be how much? Gamma B grad phi B dot A B, right. That is the total transport of phi through the boundary phase, minus what would be the one going through the primary direction? That will be gamma B upon del xi B, AB dot AB upon AB dot E xi grad phi B dot E xi times delta xi B, okay. We can again calculate it this way. Fine. Now, I do not have gradient of phi on the face, boundary face, to calculate as a linear interpolation of the two cells, right. So, I would make an assumption here, and I would say that the gradient of phi on the boundary phase would be just equal to gradient of phi of the cell C 0, okay, because I do not have a gradient on the other side. I do not have C 1 cell, right, because that is a boundary phase. So, I would make this assumption and approximation, then I can rewrite this as gamma B grad phi 0 dot A B minus gamma B by del xi B AB dot AB upon AB dot xi grad phi 0 dot xi del xi b. Okay. Grad phi 0 is already calculated, right, somehow through some gradient calculation method. Fine, so far so good. This is very much same as the how we dealt with the interior faces, any interior face. Okay. Now, let us look at a specific boundary condition. So, this is how we discretize the boundary fluxes. Now, let us look at a specific boundary condition. Let us call it as the Dirichlet boundary condition. Okay. That means, we are talking about Dirichlet boundary condition. What is a Dirichlet boundary condition in this context? What is specified? Phi b would be known. This means phi b known, right? This will be known. Okay. If this is known, let us look at what will happen to the primary gradient term. So, we come back here. This is the coefficient, right? What will be the contribution of the primary gradient? Where all the primary gradient terms go? Phi b is known, right? This is known. This is not an unknown anymore. Phi 0, is it unknown or known? Unknown, right? This is unknown. So, what will be the contribution of primary gradient to what terms? AP, because there is a phi 0 term. So, there will be a contribution to AP, which is about this value. This value, what do you usually call? A B, right? A sub B is what we call. This is AB. AB contributes to AP. What else will be there to B term, right? What will be the B term? AB times phi B known would go to B, right? Because this is known now. This is a Dirichlet boundary condition. Everybody okay with that? Yes? Okay. That means, this is contributing to two terms, that is AP and B, right, to both of them. What about the other term, that is the secondary gradient? Where will this guy go? SGB. Secondary gradient on the boundary, where will this term go? Goes to the B always, as it is. Okay. Fine. So, that means, we can now ready to write the discrete equation. That means, if you have a Dirichlet boundary condition, we know what is phi b is phi b known, right. This is a known value. Then we are ready to write the discrete equation. Okay. So, what would be the discrete equation? It would be, we want it to come and fit in the same form, that is AP phi 0 equals sigma A and B phi and B plus B, right. We always want it to come and fit in the standard form. Now, what will be A and B? A and B would be same as before, right. So, this would be gamma f by del xi f AF dot AF by AF dot xi for all the neighbors. But what are all these neighbors now? These are only the interior faces. So, that means 1, 2 all the way to m minus 1 if you have one boundary face. If you have two boundary faces, it will be different, right. If you have a corner cell where there are two boundary faces, you have to say m minus 2 and then include those boundary effects. Okay. Fine. Let us say we are talking about now one cell here. What about AP? So, these are the interior faces only. What about AP term? AP would be summation of A and B, where NB goes from 1 to all the way to m minus 1 plus AB. Okay. This goes to, if you have one boundary face, this will go to AB. What else? Minus SP delta V 0. That is all, right. That is all will be there. Okay. What about the B term? B term would have SC times delta V 0, source term. What else? Secondary gradient coming from interior faces, right, as before. That means sigma NB SG F, where NB are the interior faces again. Let us call it as NB interior. What else? AB phi B, okay, that is plus or minus? Plus, Okay, this is A B phi B. Anything else? What about the secondary gradient for the boundary phase? Would that be there?
Yes.
That should also, would that be in B here? Yes. That means plus SG boundary, right, if you have one boundary phase, or sigma SGB if you have multiple boundary phases. Fine, is that okay? Of course, I did not write what is AB. AB itself is similar to the A and B. AB would be gamma B by del xi B, AB dot AB by AB dot E xi, right? That is your AB. Fine, is that okay? Everybody, any questions on this? Yeah.
Sir, when we calculate SGB for the, we use the previous iteration value for phi. So gamma grad phi we have to calculate.
Gamma grad phi.
For the boundary.
Yeah, essentially this has to be calculated. Gamma B grad phi B dot AB.
So that means we use the previous iteration.
Yes, we use the previous iteration. Grad phi would be the previous grad phi. You would use the previous iteration values of phi and calculate the gradient, right? But the assumption we are making here is that grad phi B would be equal to grad phi 0. That is what I am making here. We will again discuss this thing, the efficacy of this approximation, right? We will discuss it a little later. Fine, is that clear? As of now, we somehow through some method know the value of the gradients of the phi, okay, which we can use here. That's the idea here. Questions? Other questions? No? Fine? Clear? So, we have looked at Dirichlet boundary condition. Then let us look at the boundedness properties. Okay. What about so in the absence of source terms S equal to 0, what will be AP? Relation between AP and sigma A and B. AP equals sigma A and B, or is it greater? What are the neighbors here? What constitute as neighbors? Only the interior, right, not the boundary, right. When you write the equation, you do not have the coefficient coming from the phi B in the matrix, because that guy went to the right hand side. So, what is AP? Is it equal to sigma n B? No, it is greater than sigma n B by an amount of AB. This is same as nothing new, right. This is same as the Dirichlet boundary condition for structured Cartesian meshes that we have seen before. So, that means AP is greater than sigma n B. So, this satisfies your Scarborough inequality. Okay. So, this satisfies Scarborough inequality. Fine, very good. What about boundedness? So, S equal to 0, S equal to 0 is your AP phi P equals sigma n B phi n B plus B. Is B 0? S is 0, so this guy goes to 0. Is B 0? Okay, we can leave this guy, but this guy still contributes to the boundedness, right, because AB is included in the calculation of AP and also this one. So, we can think of this as, if it is bounded, it can be bounded by the phase value as well as by the cell neighbor values. But what is the other one that is preventing us from having boundedness? Secondary gradients of the phases, interior phases and the boundary phase. Okay. As a result, phi 0 is not assured to be bounded by cell neighbor values. Okay. Fine. Okay. All right. That means we have done discretization. Then you can of course extend this concept to, if you have unsteady diffusion, right, on non-orthogonal meshes. Can you extend this concept? Ultimately, the equation we are working with is AP phi P equals sigma n B phi n B plus B, right. Can you extend this concept to unsteady, right, all the explicit, implicit and Crank-Nicolson methods? Okay, it can be done. What about gamma F interpolation? Can that be performed in this case using a harmonic mean, right? You have to find the distances and calculate what is gamma f interpolation. Okay, I am writing all this because I am not doing all this, right? All this will be your work for you. You have to do it. Okay, verify later on. Okay, what else? This is the most exciting part, right? Gamma f interpolation. What else? Source term linearization. Okay, so source term linearization can also be, will remain the same as before. What about under relaxation, right? Can you perform under relaxation for these cases? Yes. So, under relaxation can also be performed on this for non-orthogonal meshes, right? So, you can verify that all these things can be done. Okay. This is for you to verify or extend. Okay, to all these different scenarios. Okay. We have now left over one more thing. What is that? Sorry? Stability analysis, of course, you can also do. What else? Let us write stability analysis. Okay. But stability analysis would not be very different, right? It probably won't be, it's probably not very easy to do because you have now unstructured meshes, right? We just discussed that if you have a uniform 1D structured mesh, it can be done easily, right? So, this is probably not very easy to do, but of course, you are welcome to check and see where you get stuck or something. What else? I have only done it for a Dirichlet boundary condition, right? We have two other boundary conditions. What are those? Neumann boundary condition and mixed boundary condition. Okay. So, you will extend the concept to include these two boundary conditions also for non-orthogonal unstructured meshes. Okay. Now, I would not leave you alone like that. So, what will happen in the context of Neumann boundary condition? Let us go back and see. Let us say if you have a homogeneous Neumann condition, what will be the condition that is specified? What will be specified if you have a Neumann, homogeneous Neumann? Grad phi will be specified, right? Grad phi will be specified in which direction? In the z direction. So, what will happen to the primary gradients? Primary gradients is what is the term that goes away, right? What about the secondary gradients? Would that remain? That will still remain, right? So, that will still remain. That is how you would implement, right? Now, how do you do for mixed boundary conditions? Yeah. Okay, why flux will be known? We are assuming that that is what is given to us. Usually, if we have a phase, it would be given in the direction of the normal to the phase, right? That is kind of a, if you have, let us say, insulation or something, the flux going in that direction would be 0, right? In the direction of A, B would be 0, right? That is minus k dt d xi would be equal to 0, right? But it need not be known in the same direction, right? If it is not known, what would you do? If it is given in a, let us say, in general you would be given, what would you do in that context? Take components and then work with this. What about mixed boundary conditions? Let us say if you have convection happening on the particular phase, how would you implement it now? You remember the concept how we have done? What did we do? You get rid of phi b from the equations, right? You have to go to phi 0 and phi free stream, phi infinity, and then work with the equations. Fine. Okay. So, all of these is for you to check and verify and extend. Okay. All right. Questions till now? Neumann boundary condition. Okay. We know the primary gradient. Okay. Right. So, you have to calculate the total and then subtract off the side direction, right. So, how do I deal with secondary gradient? Essentially the question is, if I have a Neumann boundary condition, how do I deal with SGB term, right. You would calculate what is grad phi 0 for the cell, right, and you can also calculate the primary gradient, right, that is phi xi b, right. Now, that is not the same as what is given. right. What is given to you is in the direction normal to the face, right. So, that you have to check and perform, right, but SGB would still remain, right, unless unless that boundary cell is orthogonal. How do you calculate secondary gradient of B? Primary, the total minus the primary, right, that concept is the same thing here. Yes.
Suppose we have a domain has a plane with the fluxes entering normal to the plane.
Mm.
So in that case, suppose the domain is divided into unstructured mesh.
Mm.
So that plane will be having many cells whose boundary is on the plane.
Mm-hmm.
And each cell is unstructured, so each E zeta will be in different directions.
Yes.
So in that case, the fluxes definitely along say minus 8L.
Mm-hmm.
But E zeta is different, so you can't tell, you can assume.
Yeah, true, that is true. It depends on the cell. It varies from phase to phase, but your boundary condition is already known to you. How the flux is, in what direction the flux is, right. You are applying some q bar. Now, this q bar is known to you, right. It has a certain ijk components. From there, you have to take a dot product with your particular phase direction a b bar and then calculate. So, it is not that your primary gradient will always be 0, right. So, that is possible. So, that is where you have to look at and see how this comes up, right. May not be in the direction of xi, right. Q bar is perpendicular to the is along the normal to the face, but it is need not be in the direction of xi, because xi is defined by how your cell is positioned, right. If the line connecting the cell centroid to the face centroid is along the direction of xi, along the direction of AB, then you do not have an issue, but otherwise you will get the secondary gradient and all these things, right. Otherwise, it will be like if you have an orthogonal cell, your secondary gradient will go to 0, right, automatically xi dot En will go to 0 and you do not have to do anything there, fine. Other questions? Okay. So, then that kind of finishes the discussion on diffusion equation per se, on unstructured non-orthogonal meshes as well. Okay. We have one more concept which we have not covered, that is calculation of the gradients, right, that is what we have introduced. So, we have this small topic on the calculation of gradients for the dependent variable, that is how do I calculate grad phi. Okay. There are several methods available. We will look at couple of methods in this particular course and see how grad phi can be calculated. Okay. That is gradient calculation will be our next topic that we discuss, then that finishes our chapter on diffusion. Okay. After this, we will move on to the convection chapter, fine. So, all right. So, in the next lecture, we will look at calculation of gradient for the dependent variables. Okay. Thank you. See you guys in the next lecture.